So in my first two videos, I think it was, we went over a ton of examples on building our table of Laplace transforms, but we only went one way, right? So we started in the t domain and we transformed that into a function capital F of s, right, in the s domain. So if, all right here, if f of s is the Laplace transform of some function f of t, right, then that must mean that f of t, the function itself, is equal to, it's called the inverse Laplace, so it's L to the negative 1, right? That's kind of the sign for inverse in math of capital F of s. So Laplace transforms are a linear reversible process, a linear reversible operation. Okay, so if we go one way, if we say capital F of s, right, is the Laplace transform of f of t, if we take the transform of some function f of t, right, we're going to get the capital F of s. But we can go the other way and say, if we want some function f of t, we have to take the Laplace transform of capital F of s, but inversed. So the inverse Laplace transform, we're going the other way now, is just going to be lowercase f of t. Okay, so I said it's reversible, but I also said it's linear. What linear means is if we have the Laplace transform of, say, like c1 f of 1 t plus c2f of 2 t, right? So this is like your sines and cosines, just two functions adding together. If we take the Laplace transform of both of them, the sum, this is just going to equal c1, because that's a constant, right? That's what the c stands for. L of f of 1 t, right? Plus c2 times the Laplace transform of f of 2t. So what this function, or what this kind of line here really suggests, is that Laplace transforms behave a lot like integrals. And it's no wonder, because Laplace transforms are integrals. Okay, so this is called the property of additivity. If we're taking here, I'll write f of t. If the function f of t, say, is, I don't know, t squared plus 1, right? If we were to integrate this, right, this is the same as the integral of t squared plus the integral of 1. Okay, so just like that, with integrals, the Laplace transform, if we were going to take the Laplace transform of f of t, right, this would be the Laplace transform of t squared, right? And we can break this up, so plus the Laplace transform of 1. So Laplace transforms are additive. If we apply this Laplace operator on an equation, right, we have to apply it on everything, and we can split it up because they're additive. Okay, so now that you know that, let's just kind of write a table here. Let's build our table. So the Laplace transform of e to the lambda t, right, that was equal to 1 over s minus lambda, and I'll move this over a bit. Okay, so now if we go the other way, right, that must mean the inverse Laplace of 1 over s minus lambda is equal to e to the lambda t, and that's 100% true. Okay, so we kind of generalize this above, right? This is, our f of t is just e to the lambda t. That equals our capital F of s, which is 1 over s minus lambda, right? An antiderivative function in terms of s. But if we went the other way, if we took the inverse Laplace of 1 over s minus lambda, right, f of s, we're just going to get f of t back. So we're kind of going back and forth there. It might seem intuitively obvious, but it's an important property that we have to kind of really harness before we can move on into solving differential equations with the Laplace transform. Okay, same kind of thing here. The Laplace transform of 1 was equal to 1 over s, right? If we went the other way, right, if we took the Laplace transform of capital F of s, so 1 over s, this is equal to 1. Okay? And the reason we're going through all these is because, like, if you go from the t domain into the s domain and just leave it there, you can't solve any differential equations like that because you have it in terms of s, not in terms of t. So knowing how to go back and forth is super important, and we're going to do examples where we recognize what kind of transform to use. Okay, so remember with t to the n, this was n factorial over s to the n plus 1. Now if we went the other way, right, we could write the inverse Laplace of n factorial over s to the n plus 1, but typically, like, it's going to be hard to recognize when you have a function of n factorial on the top and then over s to the n plus 1. So for example, if it was like 7 factorial over s to the 7 plus 1, so over s to the 8, like, I don't even know what 7 factorial is, and when is it ever going to happen where you have exactly 7 factorial on the top and exactly s to the 8 on the bottom? Not very often. So the way we write this, right, as more of a general way to see functions, a more common way to see them is 1 over s to the n, right? And just with a bit of manipulation, I'm not going to derive how we figure this out, but it's a similar idea. That's going to equal not t to the n, but t to the n minus 1 over n minus 1 factorial. So these two sides here are completely equivalent. We just kind of rearrange some stuff. It's not a super hard derivation, but it's just not really. Some things are worth proving, but I don't think this is, okay? So like I said, professors are going to give you these tables. I'm just showing you what we've done ourselves already. So if there's something that you're not completely sure about, we can just go back to the last video and kind of take a look there. Okay, remember when we did a cosine, we got s over s squared plus b squared. Now if we go the other way, if we take the Laplace transform, inverse of that, I keep forgetting my inverse signs, Laplace transform inverse of s over s squared plus b squared. Right, we're just going to get cosine bt back. So nothing weird going on there, right? This is our f of t, f of s, f of s, f of t. So we're just kind of going back and forth there. Now with sine, it's a little different. Okay, and the reason it's a little different is because, remember we got, like, I'll write it here, Laplace transform of sine bt, remember, that was like cosine bt, except instead of s on top, it was b over s squared plus b squared. So it's going to be really rare where you see a b on the top, b squared on the bottom, adding into s squared. Okay, so just like with this one up here, where it's rare to find n factorial over s to the n plus 1, you're not really going to see this much in math. It's going to be hard to recognize. Okay, so what we do is, instead of having b on the top, we just want 1, because it happens all the time where we see a function that's 1 over s squared plus, for example, 9, right? In that case, b would be 3. But you don't see it all the time where the top is just the square root of b squared, right? So you're going to see this a lot less than just 1 over that. Okay, so instead of writing the b there, we divide both sides by b. So if we divide this here by b, right, we get 1 over s squared plus b squared. So the inverse Laplace of 1 over s squared plus b squared instead of b over, that just equals, well, if we divide one side by b, we have to divide by the other side by b. So if this is our f of t, it's going to be 1 over b sine bt. Okay? And those are kind of the 5 we're really working with at this point. That's kind of the table we've built. So I'm not going to go on in this video to do examples. I'm going to make a separate one, but this is kind of just a recap of the properties of the Laplace transform and what the inverse Laplace transform is. So if we have f of t, take the Laplace transform of that, we get capital F of s, right? We're in the s domain. If we want to go backwards to get f of t back again, we just take the inverse Laplace. Okay? And this is going to be crucial when we're solving differential equations. So, like, actually knowing, like, the implications of this, I don't expect you to, but just kind of knowing the idea that it's a reversible linear process, and also if we're taking the Laplace transform of a sum of functions, right, it's a linear process, a linear operator, so we can split that up into the Laplace transform of one plus the Laplace transform of the other, and we can also factor out constants like I indicated here. Okay, and then I just wrote kind of the table we built. And these kind of, the middle one and the bottom one on the right side, these are just more general ways that you'll find it in nature, okay? So I think doing this is a bit of a favor, right? Because if we just left it as like n factorial over s to the n plus 1, and then b over s squared plus b squared, it wouldn't be as useful. So this is a much more useful form. So I'll see you in my next video to talk a bit more about how we can actually compute these and solve them with real examples.